Chi-square independence test. Expected frequencies for an independence test. In a chi-square independence test, the expected frequency for each cell is found by using the formula E equals R times C divided by N, where R is the row total, C is the column total, and N is the sample size. Distribution of the chi-squared statistic for a chi-square independence test. For the chi-square independence test, the test statistic chi-square equals the sum of O minus E parentheses squared divided by E has approximately a chi-square distribution if the null hypothesis of non-association is true. The number of degrees of freedom is R minus 1 times C minus 1, where R and C are the possible values for the two variables under consideration. Chi-square independence test. Purpose: to perform a hypothesis test to decide whether two variables are associated. Assumptions: 1. All expected frequencies are 1 or greater. 2. At most 20% of the expected frequencies are less than 5. 3. Simple random sample. Chi-square independence test. Step 1. The null hypothesis and the alternative hypothesis are respectively H sub 0, the two variables are not associated. H sub A, the two variables are associated. Step 2. Decide on the significance level alpha. Step 3. Compute the value of the test statistic. Chi-square equals the sum of O minus E parentheses squared divided by E, where O and E represent observed and expected frequencies respectively. Denote the value of the test statistic chi-squared sub 0. Chi-square independence test using critical values. Step 4. The critical value is chi-squared sub alpha with degrees of freedom equal R minus 1 times C minus 1, where R and C are the number of possible values for the two variables. Use the chi-square distribution to find the critical value. The area to the right of the critical value chi-squared sub alpha is labeled alpha, and that is reject H sub 0. To the left of chi-squared sub alpha is do not reject H sub 0. Step 5. If the value of the test statistic falls in the rejection region, reject H sub 0. Otherwise, do not reject H sub 0. Step 6. Interpret the results of the hypothesis test. Chi-square independence test using p-value approach. Step 4. The chi-squared statistic has degrees of freedom equal R minus 1 times C minus 1, where R and C are the number of possible values for the two variables. Use the chi-square distribution to estimate the p-value or obtain it by using technology. Chi-square sub 0 is our test statistic, and the p-value is the area to the right of the test statistic. Step 5. If p is less than or equal to alpha, reject H sub 0, otherwise do not reject H sub 0. Step 6. Interpret the results of the hypothesis test. Example using critical values. The contingency table gives a cross-classification of a random sample of values for two variables x and y of a population. A. Find the expected frequencies. B. Determine the value of the chi-squared statistic. C. Decide at the 5% significance level whether the data provides sufficient evidence to conclude that the two variables are associated. For x, I have the columns capital A and capital B. For y, I have the rows lowercase a, lowercase b. For lowercase a, capital A, my result is 30. For lowercase a, capital B, the result is 20. For lowercase b, capital A, the result is 40. For lowercase b, capital B, the result is 10. Find the expected frequencies. The first thing we need to do is find the total of our rows and the total of our columns. Starting with lowercase a, I have in that row 30 and 20 for a total of 50. Lowercase b, that row has 40 and 10 for a total of 50. Moving to my columns, capital A has 30 and 40 for a total of 70. Capital B has 20 and 10 for a total of 30. If I total my rows, 50 plus 50 is 100. If I total my columns, 70 plus 30 is 100. Now that I have my totals, I can calculate the expected frequencies. E equals R times C divided by N. So I want to create a table similar to the table that my original data is in, where my X are the columns, capital A, capital B, and my Y are the rows, lowercase a, lowercase b. So I want to start by finding the expected frequency for lowercase a, capital A. The total for lowercase a is 50, and the total for capital A is 70. N equals 100. To calculate, I have 50 times 70 divided by 100, which is 35. Now I want to find the expected frequency for lowercase a, capital B. The totals for lowercase a is 50, for capital B is 30. 50 times 30 divided by N, which is 100, gives us a value of 15. Next, I want to find the expected frequency for lowercase b, capital A. The total for lowercase b is 50, capital A is 70. 50 times 70 divided by 100 gives us a value of 35. Now I want to find the expected frequency for lowercase b, capital B. Lowercase b has a total of 50, capital B has a total of 30. 50 times 30 divided by 100 gives me a value of 15. Next, we want to determine the value of the chi-squared statistic. Step 1, find h sub 0 and h sub a. H sub 0, the two variables x and y are not associated. H sub a, the two variables x and y are associated. Step 2, decide on the significance level alpha. We were told alpha is 0.05. Step 3, compute the value of the test statistic chi-squared. We have a table with our observed frequencies where lowercase a, capital A is 30, lowercase a, capital B is 20, lowercase b, capital A is 40, lowercase b, capital B is 10. And we have the expected frequencies that we just found. Lowercase a, capital A is 35, lowercase a, capital B is 15, lowercase b, capital A is 35, lowercase b, capital B is 15. To find our test statistic chi-squared, we are going to go to our calculator and use our matrices function. The matrix is above x to the negative 1, so second x to the negative 1 takes us into our matrices. We want to go to Edit, Matrices A, press Enter, and we want a 2 by 2 matrices. So I type 2, arrow, 2, Enter. For my first value, I'm going to type 30, which is lowercase a, capital A, Enter. Then lowercase a, capital B, which is 20, Enter. Lowercase b, capital A, which is 40, Enter. And lowercase b, capital B, which is 10, Enter. So I have my observed frequencies in matrix A. I'm going to type second, matrix again, go over to Edit, down to B, Enter, and this is going to be the expected frequencies. So it is a 2 by 2 matrices, Enter. Lowercase a capital A is 35. Enter. Lowercase a capital B is 15. Enter. Lowercase b capital A is 35. Enter. And lowercase b capital B is 15. Enter. I'm going to type second in mode to quit and go back to my main screen. Now I want to find chi-squared. Stat, over to tests, and I want the chi-squared test. Enter. Now I have observed with matrix A, expected matrix B, which is what I want. But if it didn't say A, I could go to second matrix and choose number 1, A, enter, and it types it in for me. I'm going to go down to calculate, enter, and my test statistic, chi-squared, 4.7619. Rounding to 2 decimal places, chi-squared equals 4.76. Identify the critical value. Step 4. The critical value is chi-squared sub alpha with degrees of freedom equal r minus 1 times c minus 1, where r and c are the number of possible values for the two variables. Use the chi-squared distribution to find the critical value. We know that alpha is 0.05. We want to find the chi-squared value that matches an area of 0.05. My rejection region is to the right of chi-squared sub alpha. I have 2 rows and 2 columns, so when I substitute for the degrees of freedom, I have 2 minus 1 in parentheses and 2 minus 1 in parentheses. 1 times 1 equals 1. Going to my table, my first row is degrees of freedom 1. I want the column that has chi-squared sub 0.05, and they cross at 3.841. Chi-squared sub alpha equals 3.841. Step 5. If the value of the test statistic falls in the rejection region, reject H sub 0. Otherwise, do not reject H sub 0. The critical value chi-squared sub alpha is 3.841. Our test statistic chi-squared equals 4.76, which is to the right of our critical value, and that falls in the rejection region. Reject H sub 0, the null hypothesis. Step 6. Interpret the results of the hypothesis test. The data provide sufficient evidence of an association. Example using p-values. Preventable chronic diseases are increasing rapidly in some regions, particularly diabetes. The contingency table shows cross-classification of educational attainment and diabetic state for a random sample of 1,647 people in a region. HS is high school. At the 1% significance level, do the data provide sufficient evidence to conclude that an association exists between educational level and diabetic state for the region? In our table, we have 2 rows. Diabetes, no diabetes. Then we have 4 columns, less than high school grad, some college, college grad. We also have a total for our rows and our columns. People with diabetes that have less than a high school education, 20. No diabetes, less than a high school education, 407, for a total of 427 under less than high school. High school grad with diabetes, 17. No diabetes high school grad is 360. High school grad total, 377. Diabetes, some college, 33. No diabetes, some college, 386, for a total of 419 under some college education. College grad, diabetes is 33. College grad, no diabetes is 391, for a total of 424 under college grad. The total for diabetes is 103, and no diabetes is 1,544. 103 plus 1,544 equals our sample size of 1,647. The total for our columns, 427 plus 377 plus 419 plus 424, is also the sample size, 1,647. Find the expected frequencies. We have the same table. Calculate the expected frequencies. E equals row times column divided by the sample size n. So I start with my table where I have diabetes and no diabetes for my rows, less HS, HS grad, some college, college grad for my column headings. So I'm going to start with the total for less than HS and the total for diabetes. So I have 103 times 427 divided by 1,647, which gives us 26.70. Next, I'm moving to diabetes high school grad. The total for my diabetes row is 103. The total for high school grad is 377. 103 times 377 divided by 1,647 is 23.58. Next, I'm going to move to diabetes and some college. The total for diabetes is 103. The total for some college is 419. 103 times 419 divided by 1,647 is 26.20. Next, we have diabetes and college grad. The total for diabetes is 103. The total for college grad is 424. 103 times 424 divided by 1,647 is 26.52. Moving to the next row, no diabetes, I want to start with less HS. The total for no diabetes is 1,544. The total for less than high school is 427. 1,544 times 427 divided by 1,647 gives us 400.30. Next, no diabetes, HS grad. The total for no diabetes is 1,544. The total for HS grad is 377. That gives us 1,544 times 377 divided by 1,647. That answer is 353.42. Next, some college, no diabetes. The total for no diabetes is 1,544. The total for some college is 419. 1,544 times 419 divided by 1,647 is 392.80. Next, college grad, no diabetes. The total for no diabetes is 1,544. The total for college grad is 424. 1,544 times 424 divided by 1,647 is 397.48. Determine the value of the chi-squared statistic. Step 1. Find h sub 0 and h sub a. H sub 0, the two variables, education level and diabetic state, are not associated. H sub a, the two variables, education level and diabetic state, are associated. Step 2. Decide the significance level, alpha. Since it was 1%, alpha is 0.01. Step 3. Compute the value of the test statistic chi-squared. First, we want our table of observed frequencies. Then we need our table of expected frequencies that we just found. Use the matrix function in our calculator. Second, matrix will take us to our matrices. We want to edit our matrices. I'm going to use A for the observed frequencies. Enter. So I have 2 rows and 4 columns. So I'm going to type in the observed frequencies. I'm using my row for diabetes, 20, enter, 17, enter, 33, enter, 33, enter. Then I'm going to use the values for no diabetes, 407, enter, 360, enter, 386, enter, 391, enter. Now I'm ready to create the matrix for expected frequencies. Second, matrix, over to edit. I'm going to use matrix B for my expected frequencies. Enter, 2, enter, 4, enter, 2 rows, 4 columns. Starting with diabetes, I have 26.7, enter, 23.58, enter, 26.2, enter, 26.52, enter. Now I want to type in the row no diabetes, 400.3, enter, 353.42, enter, 392.8, enter, 397.48, enter. Second, quit gets me back to my main screen. Now I can find chi-squared. Stat, over to tests. I want to use chi-squared test. Enter. My observed value is A. My expected value is B. Calculate. Enter. And my top value is my chi-squared value, 7.3239. I want to round that to 3 decimal places. Chi-squared equals 7.324. Identify the p-value. Step 4. The chi-squared statistic has degrees of freedom, parenthesis r-1 times parenthesis c-1, where r and c are the number of possible values for the 2 variables. Use the chi-squared distribution to estimate the p-value or obtain it exactly by using technology. We have already found our chi-squared value, 7.324. Our p-value is to the right of our test statistic. First, I have to find my degrees of freedom. I have 2 rows and 4 columns. 2 minus 1 times 4 minus 1. 2 minus 1 is 1. 4 minus 1 is 3. 1 times 3 is 3. So going back to our calculator, my p-value is 0.062259. I want to round that to 3 decimal places. P equals 0.062. Step 5. If P is less than or equal to alpha, reject H sub 0. Otherwise, do not reject H sub 0. So I want to compare my p-value of 0.062 to alpha, which is 0.01. 0.062 is greater than 0.01. The p-value is greater than 0.01. Do not reject H sub 0, the null hypothesis. Step 6. Interpret the results of the hypothesis test. The data do not provide sufficient evidence of an association. To recap, chi-square independence test. Expected frequencies for an independence test. The expected frequency for each cell is found by the formula E equals R times C divided by N. R is the row total, C is the column total, and N is the sample size. Distribution of the chi-squared statistic for a chi-squared independence test. The test statistic is chi-squared equals the sum of O minus E parentheses squared divided by E, where O is the observed frequency and E is the expected frequency, and the number of degrees of freedom is in parentheses R minus 1 times in parentheses C minus 1, where R is the number of rows and C is the number of columns.